Hello, this is the third lecture for Thermodynamics on Chapter 16 if you're talking about Zumdahl, and Chapter 19 if you're talking about Brown. And we have been talking about energy and exothermic versus endothermic and whether those tend to be spontaneous, and entropy and how that contributes to spontaneity, and the second law of thermodynamics, which says the entropy of the universe always increases. And so really we're kind of in a mess right now because we haven't figured out what exactly causes a reaction to be spontaneous, but we know lots of little pieces about it. So in this lecture I'm going to try and tie all that up so that you actually know what to do with all this information. So to restate our current state of confusion, we want to know what it is that determines whether a reaction is spontaneous. And a couple of things that we've learned are, number one, that if a reaction is exothermic, it's more likely to be spontaneous. Just because if a reaction is exothermic, that means that it contains energy at the beginning, and then it can lose it to the surroundings. And so that's kind of an easy deal, is to lose energy. Whereas if a reaction is endothermic, it's got to gain energy from the environment, from the surroundings, and that's sort of a hard deal. So it is generally observed that exothermic reactions are more frequently spontaneous, whereas endothermic reactions are less frequently spontaneous. But that's not all there is to it, because sometimes you've got endothermic reactions that are spontaneous, and sometimes you've got exothermic reactions that aren't. So there's another piece to it, which is the entropy. The thing that we know about entropy and spontaneity is related to the second law of thermodynamics, which says that the entropy of the universe always increases. But we're looking at just the system, and so it's sort of tricky. We know that the entropy of the universe always increases, but when you're dealing with a particular reaction and you can figure out what its entropy is doing, you would also have to examine the surroundings and then kind of add them together and figure out whether the entropy of the universe was increasing. So it's slightly hard, and that ends up making you have some exceptions. But in general, if a reaction causes the entropy of the system to increase, it's more likely to be spontaneous. So we've got exothermicity, which helps, and we've got an increase in entropy of the system, which helps. But which one is important, how much, and when? Is kind of the question that we're left with right now. So the first way to answer this question, I know there are two ways, is referring back to the second law of thermodynamics, which is that the universe's entropy increases always. And the way that's shown mathematically is like this. And so the entropy, which is this variable S here, the entropy of the universe is a combination of the entropy of your system and the entropy of your surroundings. And it's important to know that, where's my pen? It's important to know that about the entropy of the system that deal with the microstates. If you've got more microstates in your products as a possibility, we talked about microstates in the last lecture. You weren't here, it was just the starfish. Yeah, that guy. He knows about microstates. What you and the starfish know about microstates is that it is natural for a system to proceed toward a state that has the highest probability of existing. So what ends up happening is that there tends to be a really, really large number of ways for molecules to be in a disorganized fashion, whereas there's really only a couple of ways for them to be perfectly organized. For example, like all crowded over into one corner versus bouncing around the room, like filling the room. This is why gases fill their containers, because there's more ways for the container to be full than there are for the particles to all be over in one corner. So this thing. So the entropy of the system, this has to do with microstates, and if there are more microstates, that increases your entropy of your system. It's also important to understand that the entropy of the surroundings can be increased can be increased by adding heat. If you add heat to your surroundings, then you make your particles kind of wilder and crazier, and so they have more options. They have more microstates for what they can be doing. This tends to be more important when you start off in a cold condition. So there's a little formula. Delta S of surroundings is negative delta H over T. And this formula is really more important for meaning than for use. What it's saying is the change in entropy of your surroundings is affected by your enthalpy change, but since enthalpy change when it's exothermic is negative, you have to flip it the sign to indicate that you're increasing the entropy. And what is neat is that it's related to temperature. With this temperature being on the bottom here, when the temperature is high, it makes this a small value, and so that means your entropy change is small when it's hot. But when it's cold, you have a small number for T, and so you end up with this fraction being a large value, so the entropy change for the surroundings that's caused by this addition of heat is large when it is cold. So there we go. So these are the couple of things that you need to understand about the entropy of the universe. As you look at the microstates that are your options, which in general is, do you have more gases in your products? Because gases have got so many more microstates than solids and liquids and stuff, that's kind of what the question is just checking to see if you know. It's like, oh, are there more gases? Okay, well then the entropy of my system is increasing. And the other part is that you would have to examine your surroundings to find out, are you adding heat to the surroundings to increase the entropy of the surroundings, and how hot was it when you did that? And so that's how you would figure out the entropy of the universe, whether it was increasing or decreasing. If the entropy of the universe ends up increasing, then we can be sure that this is a spontaneous process. But it's sort of a pain to examine. You can measure your system just fine, but measuring the surroundings, like just the air and exactly what everything around is doing, is kind of practically difficult. So this is the first answer to how do we figure all this out, but it turns out that it's a huge pain. The more fun answer involves something called G, which is the Gibbs free energy, which we will look at back on our notes. The Gibbs free energy, which I know that we've already learned about enthalpy and internal energy, which are subtly different. Here's another form of energy that is subtly different. The Gibbs free energy, and here's this formula, which is both nice to discuss as a meaning formula, and it ends up getting used a lot, mathematically speaking. So the Gibbs free energy is basically your enthalpy, which is all of your energy, but you need to subtract off the worthless, crappy entropy, temperature-y energy. So what this ends up being is the energy that you can use, the energy that is free to be used for work. Gibbs free energy, it tends to be used by engineers as the value for, well, how much work can I get out of this engine, for example? And so they'll do all these calculations to figure out the Gibbs free energy, because they want to know, well, how fast can I push my pistons or whatever. So that's what it means and what it's for. And when I first learned this equation, the lady that was teaching it to me called it the going home to supper equation, which I thought was kind of cute. But my husband has informed me that in fact it stands for go hit that skunk. So I believe that this is the go hit that skunk equation.
Yeah, he wins.
So taking this equation, which is sort of the definition of Gibbs free energy, you can do some fun substitutions, which I'm not going to talk about, but they have them in your book if you really want to look at them. You will discover that the entropy of the universe, which you remember is really important for spontaneity, is equal to the opposite of delta G over T. Okay. Yes, bud. So what that means is that we know that the entropy of the universe, if it's positive, you've got something spontaneous, right? Go away. Stop. What do you... There's a little control thing here, and it's covering up my notes. There we go. So when this is positive, it is positive if delta G is negative, because we've got the opposite of delta G. So if delta G is negative, you've got negative times negative, that gives you a positive. And you can't really have a you can't have a negative T because it's kelvins, right? So so if G is negative, then this is positive, and a process is spontaneous when this is positive. So if you ever have a process that has a negative delta G, it is spontaneous. And that's easy to calculate. So that saves us the trouble of examining the surroundings that I was talking about. So really, every time you've got to do a problem or practically actually calculate this stuff for, is this going to be spontaneous? You want to find your delta G, whether it is positive or negative. If delta G is negative, it is spontaneous or thermodynamically favored. And if delta G is positive, it is non-spontaneous or not thermodynamically favored. And then what's interesting is that when these numbers, which this is the formula that I was talking about that you end up using a lot, this is the formula that you will use to determine whether delta G is positive or negative quite often. When delta G is 0, when it's going right from positive to negative, right when it hits 0, that's when the reaction is at equilibrium, and the positivity and the negativity of these two terms are just balancing each other. So that's kind of cool. There is also this type of formula, the summation formula for delta G, because there are also values in the back of your book for calculations to use with the standard state free energy stuff. So you can use that. That wasn't very clean, but anyway, you can do it with delta G the same way that you can do it with entropy and with enthalpy. And we will be doing a problem that involves calculating calculating all three of them and then combining them in this formula. So if you do have a non-spontaneous process, that doesn't mean that it won't ever go. It just means that you have to do something, which is generally provide energy for it. So can you think of an example of a non-spontaneous process that uses light to make it go?
No.
It's plants.
Well, that would be obvious, wouldn't it?
It's actually photosynthesis. Plants are not really a process.
It's a very good point.
All right, photosynthesis. You're an echinoderm. All right. So we finally have an answer, which is why it is in a star. When is it spontaneous? Thermodynamically favored. If the delta G is negative. Couple of things that affect delta G's negativity that we knew are that exothermic reactions, if you have a negative delta H, cause Gibbs free energy change to be negative E, which, look at the formula. If this part is negative, then that has a tendency to make this part negative in terms of the math. So that jives with what we understood, which is that exothermic reactions have a tendency to be spontaneous. Also, when this part is positive, because you're subtracting it, when this part is positive, because you're subtracting it, it tends to make this negative. Well, what does it mean when this part is positive? It means that the delta S is positive. It means that your entropy of your system is increasing. which we knew. We knew that you have a tendency to be spontaneous if the entropy of your system is increasing. So we are happy if this is negative and this is positive. That will make it very negative for the Gibbs free energy. In contrast, if delta H was positive, if it's an endothermic reaction, minus a negative value for entropy, so you end up minus a negative, ends up being a plus. If you have a positive plus a positive, you end up with a positive delta G, right? So that means that an endothermic reaction that decreases entropy, there is just no way that that's going to be spontaneous. However, an exothermic reaction that increases entropy is totally always spontaneous. Woo! But then you get to the two, which are, well, what if it's exothermic, but it decreases entropy? And what if it's endothermic, but it increases entropy? Who ends up winning? Well, what's the only other thing that's left? Temperature. So it ends up being that when they oppose each other, the temperature is important. So let us fill in this chart. You need to understand this chart. It's an important chart. I need my pen. All right, let's see if this eats all of my writing. So when you have got, where's my little, I have it written out for me. There we go. When you've got a negative delta H, let's say, and I'm going to make up random numbers to stick in here so that we can find values instead of having to like do it in our head without any numbers. So when you have a negative delta H, when it's exothermic, that's favorable. That's good, right? That's going to make it spontaneous. When you have a positive delta S, that's favorable. So if you've got one, if both of them are favorable, it's going to happen. So let's see, we've got delta H. Let's say that delta H is negative 100, okay? And let's say that delta S is 60. I'm just making up numbers here to stick in. And for our low temperature, I'm going to use 1 degree Kelvin, and for our, quote, high temperature, I'm going to use 10, although that's not really all that high. It's higher than 1. All right, so if you've got negative 100 minus 1 times 60, that's negative 100 minus 60 is negative 160. So you end up with negative 160 for delta G. That's negative. That is spontaneous. Okay? So that's what we expected. If both terms are favorable, yeah, it's going to be spontaneous. And even at a high temperature, you end up with negative 100 minus 600, which is negative 700. That's also so spontaneous. Woo! All right, so under those conditions, a negative and a positive, your spontaneous temperature doesn't really affect it. All right, let's flip our conditions. Let's say we've got a positive delta H and a negative delta S. A positive delta H means that you are endothermic, which is unfavorable, and a negative delta S means that the entropy is decreasing, which is unfavorable. So if both of them are unfavorable for being spontaneous, it's not going to be spontaneous. So let's stick in my random numbers that I made up. So this is going to be positive 100 and negative 60 and 1 and 10 degrees. So that's going to be 100 minus negative 60, which is 100 plus 60 is 160. And so that's non-spawn. Whereas with the high temperature, you've got 100 minus negative 60 times 10, so 100 plus 600 is positive 700, also non-spontaneous. So again, if both of them are unfavorable, then yeah, it's going to be non-spontaneous. The temperature doesn't matter. But when you get to the positive positive and the negative negative, it gets kind of interesting. So with this positive delta H, that's unfavorable, but with the positive delta S, that's favorable. Ooh, so who wins?
The higher number.
The higher number, but the part that ends up mattering, there's a point at which the temperature will affect it. So let's see, delta H, what do I have for delta H on this one? We've got 100 and we've got 60, and our low temperature is 1 and our high temperature is 10. So we end up with 100 minus 1 times 60, which is 100 minus 60, which is 40. So that's 40, which is positive. So that is non-spontaneous. However, if you make the temperature high enough, it will win. So that's going to be 100 minus 10 times 60. So 100 minus 600 is negative 500. So at some point between 1 degree and 10 degrees, it switches from non-spontaneous to spontaneous. So the temperature ends up mattering when you've got opposing favorabilities. So that's going to be spontaneous. And what this ends up meaning is that when you have an endothermic reaction that may or may not be spontaneous, if it is hot, it goes. Which makes sense, because if it's endothermic, it needs energy. When it's hot, well, there it is, so it can go. But if it's an endothermic reaction, it needs energy and it's too cold, well, then it doesn't go. So temperature ends up mattering when you're dealing with an endothermic reaction. Even though that's unfavorable, if you've got enough temperature, then you're okay. And then the last one, you have an exothermic reaction and a decrease in entropy. So that is favorable, yay, and unfavorable. And so for that, you've got negative 100, for example, and positive, hey,
Give it back.
and negative, don't do it, no, give me that, ha, and negative 60 for the delta S, and the low temperature is 1 and the high temperature is 10. So for this, your delta G is going to be negative 100 minus 60, so negative 100 plus 60, so negative 40. So at low temperatures, you have a negative delta G, which is spontaneous. Whereas, at high temperatures, you've got negative 100 minus negative 60 times 10, so negative 100 minus negative 600, or negative 100 plus 600, so that gives you positive 500, which is non-spontaneous. And the explanation for this last one is more complicated, so bear with me. All right, so if you remember when we were talking about when we were talking about this, the entropy of the surroundings can be increased by adding heat. When you're dealing with an exothermic reaction, that's what's happening. The energy is going out into the surroundings. So when you have this guy here, this exothermic reaction, it is increasing the entropy of the surroundings. Now, what we have going on here is that the entropy of the system is decreasing. And then the other part of it is that it is more important when it's cold. It's more of an effect on increasing the entropy of those surroundings when it is cold, because of that T being on the bottom. So when we look at this, when the temperature is low, it is spontaneous, because the heat that's coming out of this exothermicness is increasing the entropy of the surroundings enough to make the entropy of the universe positive. It overcomes this negative entropy of the system. When the temperature is high, there's less of an effect on the entropy of the surroundings from this exothermicness, and so it's not enough entropy increase to cause the entropy of the universe to be positive and overcome this negative entropy change for the system. Bam! There you are. And now we are going to go and do questions 3, 4, and 5. So go ahead and see what you can do on 3, 4, and 5, and I'll be back and do them with you. For you.
With you.
Hello, gentle readers. We are back, and for the observant among you, you may have noticed that the lighting is different. My assistant is missing, and I have changed my clothes. That is because it is the next day, and if you're wondering why it's the next day, you shouldn't blame me because it was you that took so long to do your problems. All right, question 3. Given the following values for enthalpy change, entropy change, and temperature, determine whether each of the following sets of data represents spontaneous or non-spontaneous processes. So what we've got is delta G equals delta H minus T delta S, and we are just going to run through all 5 of these situations with these numbers and see how that turns out for spontaneous or non-spontaneous. And you should be able to predict most of these because of the favorability of each of these numbers. So when you've got delta G for 40 kilojoules minus 130 Kelvin, and remember the S values are given in joules and you have to convert them, so that's 0.3. What we've got here is an endothermic process, which is unfavorable, and an increase in entropy, which is favorable. So who ends up winning? You have a value of 1. The guy that ends up winning is, well, first of all, is this spontaneous or non-spontaneous? This is a non-spontaneous because you have a positive value for delta G. And what ended up happening is that this is being endothermic. This is of the 2 temperatures here. This is the cold temperature, so when it is cold, endothermic processes tend not to win against a decrease in entropy, an increase in entropy. What? Yes, an increase in entropy. There we go. All right, number 2. We've got endothermic again, and a hotter temperature, and the same increase in entropy. And if you remember, when it's hotter, endothermic reactions tend to be able to be more spontaneous, and the value that you get here is -5, which indeed it is spontaneous at this negative delta G here. All right, and we've got endothermic reaction and a hot temperature, hot in quotes. I picked these numbers so that they would work out pretty for you. And a decrease in entropy, which is unfavorable. And so what we have is unfavorable and unfavorable. So this is going to be unfavorable to the tune of 85 kilojoules per mole. And here we've got -40, which is a favorable exothermic reaction, and the cold temperature, and negative entropy. And so we have them opposing again. We have got a favorable enthalpy change, but an unfavorable entropy change. And the question is, who's going to win? Well, if you think about it, if you remember that exothermic reactions are more favorable when it's cold, and we're about to do this at a hotter temperature, you end up with a value of -1. So this is, in fact, favorable. It is thermodynamically favorable or spontaneous. And the last one is -40 and temperature of 150, and it is an increase in entropy. So this is a favorable enthalpy change because it's exothermic, and a favorable entropy change because you're increasing your entropy. And so you're definitely going to end up with a nice big negative number here. So it is spontaneous indeed because of our delta G's being negative. So there you are. Question 4. Determine the temperature range in which the following chemical change is spontaneous. Now, this one is sort of long, so bear with me. The first thing that you need to do, the first thing that you need is your delta H, and the second thing that you need is your delta S, because what we're going to have to do is run the go hit that fox equation. Go hit that, no, skunk, not fox. Go hit that skunk. So we need to find out what values of G, well, we know the values of G. What values of G we're going to get out depending on the temperature. So basically what we need to do is when the reaction switches from spontaneous to non-spontaneous, it's at a specific temperature. And that switch right in the middle of it, that's when it's at equilibrium. And when the reaction is at equilibrium, delta G is 0. It's right in between a negative and a positive value. When delta G is 0, you end up having this situation where your T delta S term is equal to your delta H term. And so we need to find the switching point, the temperature at which it switches from negative to positive. So we're going to solve for T. And then after that, we need to figure out whether it's spontaneous at lower temperatures than that or higher temperatures than that. And we'll be able to kind of think that through and also use test numbers to do that. All right, but what we need first is our delta H and our delta S, and the way that we do that is that those summation formulas, and the way we use those is we go look in the back of the book in Appendix C. And here's what I got for that, which is delta H of the reaction is going to be all your products, so that's your delta H for sulfur trioxide is negative 395.2, and nitrogen monoxide is 90.37, minus all of your reactants, which you've got sulfur dioxide is negative 296.9, and your nitrogen dioxide is 33.84. And that gives you a value of negative 41.77 kilojoules. So we've got delta H of a reaction is negative 41.77 kilojoules. You should realize that that's a negative value, so this is exothermic. So the delta H is favorable for this to be a spontaneous reaction. So guess what the delta S is going to be? All right, delta S for this reaction is going to be the sum of our product entropies minus the sum of our reactant entropies, which I went to the back of the book again and got these values. And we've got 256.2 and 210.62 for sulfur trioxide and nitrogen monoxide respectively, minus your reactants, which is 248.5 and 240.45 for sulfur dioxide and nitrogen dioxide respectively. And you work that out and you get negative 22.13. Now do you know the unit? Oh, this is kilojoules per mole. The unit for entropy change is in joules per mole Kelvin. And so that means that when we go and stick this into the go hit that skunk equation, we need to convert it into kilojoules or they won't match. So that's negative 0.02213 kilojoules per mole Kelvin. All right, so we have a negative value for our delta S, so a decrease in entropy for this reaction for this system, which is unfavorable. So we've got a favorable and an unfavorable, and we need to figure out what temperature it switches from spontaneous to non-spontaneous, because it's temperature dependent in this case. So we've got to do T delta S equals delta H, and that's going to be T times negative 0.02213 is equal to negative 41.77. And we find that temperature, we find that the temperature is equal to, where's my answer? 1887 Kelvin. That's pretty hot. This is the temperature at which it switches from non-spontaneous to spontaneous, or vice versa. And so we found the point at which it's at equilibrium, and now we need to figure out which side it's spontaneous and which side is non-spontaneous, hot or cold. And you can just think through this because we know about exothermic reactions. An exothermic reaction makes a bigger impact on systems that are cold. So I predict that at temperatures below 1887 Kelvin, we're going to end up with it being spontaneous, but above it will be non-spontaneous. So let's try a value here and stick that in and see if that's the case. So for example, a temperature that's colder than that, that's easy to do, is negative 41.77. That doesn't fit. All right, delta G equals negative 41.77 minus 1,000 degrees is colder, and negative 0.02213. And you work that out and you get a delta G of negative 19.64. So it's true, below 1887 Kelvin, for example at 1,000, your delta G is negative, which means that this is spontaneous when it's colder, and so it does make sense. Woo. All right, number 5. Calculate and explain the interaction of the contributing factors to the spontaneity of the freezing of water. All right, so freezing of water, you've got water in its liquid form going to water in its solid form. Dude. For this is freezing, and there's a particular value that I don't think I've actually talked about, so don't be surprised if you were confused by this one. We need to know the change in energy for when water freezes. We know that this is going from liquid to solid, so it's from hotter to colder, so it's got to release energy, so it's an exothermic process. But there's a term for the amount of energy it takes something to melt or freeze, and it's called the heat of fusion. And in the back of your textbook, in Appendix C, I think one page before, they've got properties of water listed, and the heat of fusion is listed as delta H of fusion for water is negative 6.008 kilojoules per mole. And so that's saying that every time you freeze a mole of water, you release negative 6 kilojoules. All right. So what do we do with this value? We need to also do the go hit that skunk equation for this problem here, which means that we need to know the entropy change for liquid to solid for water here. And the way that you do that is I went to the back of the book and I was like, where's the solid water in my list of things? And it's not there because in the appendix, those are at standard state, and standard state is 25 degrees Celsius, room temperature. You don't have solid water at room temperature, so it's not there. But then I realized that what you can do is use this equation, which is that your entropy change is equal to your enthalpy change over temperature, which is that formula that indicates that the heat contributed by your enthalpy change, and depending on what temperature it is, that'll change the entropy of the surroundings. So that is maybe a little bit harder than it needed to be, but it makes sense. So 6.008 kilojoules, and this is just going to be in kilojoules real quick because we're going to have to use it anyway as kilojoules when we use the go hit that skunk equation. And the temperature that we're talking about is at 0 degrees Celsius, which is 273 Kelvin. And what you end up with is that the entropy change for freezing a mole of water is negative 22.0 joules per Kelvin. And they actually did this in your book in section 19.2. So we have our delta H, we have our delta S, and we can now calculate our delta G by going, okay, when we're talking about this process from liquid to solid, what we want to find out is when does it switch from spontaneous to non-spontaneous. And so again, that's at equilibrium, delta G is 0. So then you end up with delta H equals T delta S. And that is the case. And folks, we know what temperature this happens at, but let's calculate it. The delta H is negative 6.008 kilojoules, and the temperature we're looking for, and the delta S is oh, I did that wrong. No. I have the answer written in joules. It should have come out in kilojoules. Negative 0.022 kilojoules per mole Kelvin. There we go. Temperature times negative 0.022. And what we find is that the temperature at which the freezing of water switches from spontaneous to non-spontaneous is 273. I know you were thinking 0, weren't you? So this is the temperature at which it switches, which in Celsius is 0. Ta-da! We have just calculated something that we all knew already when we were children. And what's neat about this is that then we can go, okay, well, let's figure out which side of this is spontaneous freezing and which side is not spontaneous freezing. And so we can go and stick in, let's say, 272 and 274 and see what we get. So we've got negative 6.008 minus slightly colder than that is 272 times negative 0.022. And what that gives you is, where's my answer? Negative 0.024 kilojoules per mole. So what's cool is, at a slightly colder temperature than 0 degrees Celsius, delta G is negative, which means it's spontaneous. So what we have just figured out is that when it is colder than 0 degrees Celsius, water freezes spontaneously. And when we do it with 274 degrees Kelvin, slightly warmer, we end up with 0.02 kilojoules per mole, a positive delta G, and that means that it's not spontaneous. So that means that we've just calculated that when water is slightly warmer than 0 degrees Celsius, it does not freeze spontaneously. In fact, if you switch the reaction the other direction, it will go spontaneously in the other direction at this temperature. So that means that when it's warmer than 0 degrees Celsius, it will melt. All right, so that is it. Thanks, folks.